So, hello everyone. So, after a very long time, we are going back to online class, right? അപ്പോൾ നമ്മൾ സെക്കൻഡ് ചാപ്റ്റർ തുടങ്ങിയിട്ടുണ്ടായിരുന്നു. അതിനകത്ത് we have divided the chapter into three parts. There, ആദ്യത്തെ പാർട്ടിൽ വർക്ക് ആണ് ഡിസ്കസ് ചെയ്തത്. ആൻഡ് ഇൻ ദ സെക്കൻഡ് പാർട്ട് എനർജി. എനർജിയിൽ തന്നെ kinetic energy, potential energy, right? So, we have done until kinetic energy. Now, what we have left in this chapter is to talk about potential energy. Okay. So let's quickly go through what we have discussed until now. So at the beginning of this chapter, we discussed about time-dependent forces, time-independent forces, and then about work done by a force, and then the idea of conservative forces, right? So conservative forces, discussing the summit, we did talk about something called the conservative force field. Okay, so it is a region where conservative forces are acting. Yeah, and we know that work done by a conservative force in moving a body from one point to another is independent of the path it takes. So here, let's say we are bringing a body from point A to point B. Okay, so you can choose any path from n number of paths. You can choose any path as you wish. Okay, so when we talk about the work done here, we've been telling that work done depends on the initial and final points and not on the path which it has chosen. Either ACB hypote, ADB hypote, whichever it is, the work done doesn't depend upon the path that the body chooses to travel, force chooses to push the body. Okay. അപ്പം നമുക്ക് ഇതിൽ work done, we can write it as work as we know, F dot BR ആണ്. From A to B, we can write it like this. Okay. And since work done depends only on the initial and final points, it should be associated with some constant about this point and this point. Okay. അപ്പോൾ എന്തോ ഒരു കോൺസ്റ്റന്റ് ഫോഴ്സുമായിട്ട് റിലേറ്റഡ് ആയിരിക്കണം. അപ്പൊ അതിനെ നമ്മൾ that constant at A, the point A, let's take it as UA, and at point B, let's take it as U. Okay. അപ്പൊ അതിന്റെ ചേഞ്ച് ആയിട്ട് നമുക്ക് വർക്ക് തന്നെ കാണിക്കാൻ പറ്റും. Or we can write it like this. Okay. So ഈ U എന്ന് പറയുന്നത് അല്ലെങ്കിൽ this difference UA minus UB or UB minus UA, whichever it is, that we can call as the difference in potential energy. UA നെയും UB നെയൊക്കെ you might know, U എന്ന് denote ചെയ്യുന്നത് നമ്മൾ ഏതിനെയാണ്? Potential energy നെയാണ് അല്ലേ? So potential energy is a function of the distance to this point or the position vector at this point. Okay. So ഈ ഇക്വേഷനിൽ നമുക്ക് കിട്ടുന്നത് the difference in potential energy ആണ്. So the difference in potential energy can be denoted by this thing. Okay. I'm sorry, let's start with here. Here we have written UA minus UB. It's the reverse. When we negative sign put it, so it should be UB minus UA. Okay. Since we have reversed the signs, it should be UB minus UA. All right. So I'm going to reference point it. Potential energy on its own is not, it doesn't have an absolute value. Okay. ഏതെങ്കിലും ഒരു പോയിന്റിനെ നമ്മൾ പൊട്ടൻഷ്യൽ എനർജി സീറോ ആക്കി എടുത്തിട്ടാണ് വേറൊരു പോയിന്റിലുള്ള പൊട്ടൻഷ്യൽ എനർജിനെ പറയുന്നത്. We always talk about the difference in potential energy rather than potential energy itself. Okay. So when you say potential energy at a particular point, അതിനർത്ഥം നമ്മളിപ്പോൾ യു ബിയിലുള്ള പൊട്ടൻഷ്യൽ എനർജി ആണ് എടുക്കുന്നതെങ്കിൽ it is the difference in potential energy between UV and U5. Okay. So അങ്ങനെ എടുത്തു കഴിയുമ്പോൾ UA, you will be getting something like this. Okay. And then the difference of these two. that we'll be obtaining as this. Okay, I hope you get it. So we can write the equation to be ub minus ua equals minus of integral a to b f dot dr. Okay. So when we equate this with the work energy theorem, the equation നിങ്ങൾ മുന്നേ കണ്ടു പരിചയമുള്ള equation ആണ്. Apart from the left hand side, right hand side is familiar to you. So that is equal to, from work energy theorem, it is equal to change in kinetic energy, right? The work done is equal to change in kinetic energy. So we'll be putting that to this equation, and what we'll be obtaining as kb minus ka, change in kinetic energy, is equal to change in potential energy. Okay, and rearranging this equation, we can take the ka to this side and translating the ub to the side, which will give us ua plus k equal to ub plus k, right? And this whole total, this thing, we can call it as energy at point A. This is potential energy, and this is kinetic energy. So the sum of potential and kinetic energies at a particular point, EA and EB. So it's equal, meaning that the total energy at these points are equal. You can write it as E. So this is basically the law of conservation of mechanical energy. So using the last equation, let's find out the potential energy that's stored in a spring. Okay, so spring is attached to the origin. So we have this thing that is marked in green here. Okay, so when you give it a force and you pull it from the side, we know that the restoring force that is stored inside the spring will be equal to F equal to minus K into X, the distance, right? Distance here is the elongation. Yeah, this is from the Hooke's law, right? So we'll get the force equals this one. So when we use the last equation, നമ്മൾ തൊട്ട് മുന്നേ പറഞ്ഞിരിക്കുന്ന equation ഉപയോഗിച്ച് ചെയ്യുകയാണെങ്കിൽ change in potential energy is equal to force into displacement, force dot displacement, taken the integral. Okay, and here from A to R. Yes. Okay. So ഇവിടെ A you can take out, and what you have inside the integral is R minus R0. Okay, minus R0 dr r. So when you integrate, we'll be getting r square divided by 2. Okay, so that's what we have here. And applying the limits, we will have this one, right? And if we are to take the UR, this will be equal to this thing, the whole thing, plus UA. Okay, so UR is equal to this much, plus when you look at this part, the dotted line here, all the variables we have, they're all constants. They don't vary. Okay, yeah. R0 is a constant. It's the distance at which it was already, that. Okay, and UA is a constant because it's the potential energy at that particular point. Okay, so all these are a constant. So we can replace it by the letter C. Okay, so what we finally have is, if you are to take U R0 to be 0, വെറുതെ നിൽക്കുന്ന സ്പ്രിങ്ങിന് potential energy 0 ആണെന്ന് എടുക്കുകയാണെങ്കിൽ, then we can actually take the whole constant part to be 0. And then the potential energy stored in the spring, okay, that is equal to half K R minus R0 squared. നമ്മളിപ്പോൾ derive ചെയ്തിരിക്കുന്ന equation വെച്ചിട്ട് we can actually derive for, like, for the value, to find out the value of velocity in a uniform force field, potential energy ideal വെച്ചിട്ട്. Okay, and then we can find out the equation of motion for sorry, not equation for motion, but potential energy of inverse square field. Okay, the last equation is that is change in potential energy equals F dot dr, which you will be able to get the equation. Now let's see what's the connection between potential energy and force. Okay, so we have this basic equation u gives u equals minus of integral r to rp f dot dr, right? ഇവിടെ നമ്മളൊരു one dimensional സിസ്റ്റത്തിനെയാണ് എടുക്കുന്നത്, that the particle is moving in a single direction, right? അങ്ങനെ എടുക്കുന്ന സമയത്ത് we can take it as x, yeah. Dot ചെയ്യുന്ന സമയത്ത് fx dx is in the same direction, so fx dx itself it is, okay. So say normal particle, the movement of the particle from a position to another position, okay, and that, say this is at the position x and this is the position, say x plus del x, okay, delta x, and say this delta x is very very small, it's infinitesimally small. So say ഇത് കുറച്ചുകൂടി ക്ലോസർ ആയിട്ടുള്ള ഒരു പോയിന്റ് വിചാരിക്കും, say ഇതാണ് x, another value അത് x എന്ന് പറഞ്ഞു. So ഇവിടെ what we are going to find out is the change in potential energy. Okay, using this equation we can actually apply this one, right? U of x plus delta x, that is potential energy at this point minus potential energy at this point, that will be equal to fx dx, right? From x to x plus delta x. And since we are choosing delta x to be infinitesimally small, we can actually choose the force to be the same. Okay, ഇവിടെ നമ്മൾ ഫോഴ്സ് ഓൾമോസ്റ്റ് കോൺസ്റ്റന്റ് ആണെന്ന് എടുക്കുന്നു. So അങ്ങനെ എടുത്തു കഴിഞ്ഞാൽ we can take the force, this thing out of the integration, right? So that will obtain minus fx into ഇന്റഗ്രലിനകത്ത് dx മാത്രമായി മാറും. അതിനെ ഇന്റഗ്രേറ്റ് ചെയ്യുമ്പോൾ it is x, right? അപ്പോൾ x ന് ലിമിറ്റ്സ് കൊടുത്തു കഴിഞ്ഞാൽ these are the ones. So what we'll obtain is we'll finally obtain minus fx into delta x. So change in potential energy will be equal to this, okay? Or we can write fx equals minus delta u divided by delta x, okay? Or we can write it as minus du by dx, okay? If this has to be made infinitesimally small, okay, the change limit delta x tends to 0, this will be minus du by dx, right? So we can say that force is actually the negative gradient of potential, okay? ഇത് നമ്മൾ 3-dimensionally extend ചെയ്യുന്ന സമയത്ത് നേരത്തെ dx ആണ് എടുത്തത്, we'll have to take the dr, all right? So what we'll obtain here is fn. We're taking all the components here, it's 3-dimensional, so x, y, and z components. For r as well, we have to take the components dx, dy, and dz in I, j, and k directions respectively. So when we do this, take the dot product, it will be fx dx, fy dy, and fz dz, right? So then integrate the shape by example. Again, after the same process, we will be obtaining fx x minus du by dx fys, like this and like this, right? So ഇതിനെ നമുക്ക് we can write it as the force as the negative gradient of potential, okay? So we have earlier defined the term called del, right? Del നെ നമ്മൾ നേരത്തെ define ചെയ്തിരുന്നു dou by dou x plus dou by dou y plus dou by dou z, it's an operator, right? So rewrite it. Okay. This is the one. So here, if we have to take the curl of force, curl is another operator, okay? What we do is del cross n. This is something that we have discussed earlier in the class, right? So അങ്ങനെ എടുത്തു കഴിയുമ്പോൾ del cross F എടുക്കുമ്പോൾ what will be obtaining is I. Determine ijk rho by rho x, rho by rho y, like that. Okay. Then we know that these are the same terms repeating, right? So we know that this one will be equal to 0. Determinant will be equal to 0. So curl of a conservative force, curl of a conservative force will be 0. Okay. So when you get a problem, what you have to check whenever you get a problem, force field conservative force ആണോ അല്ലയോ എന്ന് ചെക്ക് ചെയ്യാൻ വേണ്ടിയിട്ട് നമുക്ക് എന്ത് ചെയ്താൽ മതി, del cross F എടുത്ത് നോക്കിയിട്ട് see whether it is 0 or not. Right. Potential energy പറയുന്ന സമയത്ത് we have actually discussed this. Okay. Hope you remember this. We have done problem 5. So the next concept that we have to discuss here is about stability. Okay. Then other what we are going to consider is for a simple pendulum. Okay. A simple pendulum ചുമ്മാ അതിനെ ഇങ്ങനെ വിട്ടേക്കാണെങ്കിൽ, that is you are not applying a force on it or anything, you know, and undisturbed item. This is a suspended single pendulum. Okay. This is the bob of same mass thing. And say the length this thing has is small l. Okay. അപ്പോൾ ഇതിനെ ഡിസ്റ്റർബ് ഒന്നും ചെയ്യാതെ ഇങ്ങനെ വെക്കുന്ന സമയത്ത് you know that it will be at its equilibrium position, right? And we can say that it is the stable equilibrium point. Okay. Then നമ്മൾ ഈ പോയിന്റ് slightly we have to say we are disturbing it towards this side or this side. Then we know that this will start oscillating towards both sides, right? And that when it reaches the maximum point at the side, its velocity will become 0, right? Meaning that its kinetic energy will become 0, right? Yeah. And that's when it starts to take the opposite direction. It reverses its direction. Velocity 0 on this. And then, yeah. And you know that the potential energy will be maximum at the extreme, right? So, yeah. So as it's shown here, the kinetic energy will be 0, the extreme points. And at the equilibrium position, kinetic energy will be maximum, right? Whereas potential energy നേരെ reverse ആണ്. Okay. And ഇവിടെ നമ്മൾ potential energy കാണുന്ന equation എടുക്കുകയാണെങ്കിൽ the bob is displaced to this height, right? In a vertical displacement ആണ് നമ്മൾ എടുക്കുന്നത് because the force that is acting on it is mgh, right? Gravity കാരണമുള്ള ഫോഴ്സ് ആണ് അതിൻ്റെ അകത്ത് ആക്ട് ചെയ്യുന്നത്, right? So h എന്ന് പറയുന്നത് നമ്മൾ ഇതിനെയാണ് base ആക്കി എടുക്കുന്നത്. Let's find out this distance. Okay, this is L distance. So this is L minus something, right? So let's say what it is. Triangle consider this is the theta angle, right? Upon this side will be L cos theta up to this, that is dividend it will be L cos theta, meaning that this small portion that will be L minus L cos theta, right? So we can write the potential energy to be mgh or mg into L minus L cos theta, or taking the L out, it is mgl into 1 minus cos theta, right? Theta 0 on some method. We know that we have the minimum potential energy, right? Here it is. So this is a stable point. Whereas when you have theta maximum or theta phi, say on a degree upon some method, we have an extremely unstable point, right? So when you look at this, this is a plot between potential energy and distance, Ax. So, then it's a potential energy diagram for a linear harmonic oscillator. Okay. So we know that the potential energy at the stable point is the minimum, right? It has the minimum value here. This is the stable equilibrium point. Okay, and from the equation that we derive, u is equal to half kx square, right? Yeah. So at A, say we will consider 2 points. One point A right here on this side of the curve, another point B here, and say one more point C here. Okay, and more points number at A we can see that we have to take the slope here. Okay, the point the slope slope will look like this, right? So we know that it's a positive slope. It's greater than 0, meaning that force is negative here. So force acting on a particular body that is here, okay, ഒരു ബോഡിയുടെ മുകളിൽ ആക്ട് ചെയ്യപ്പെടുന്ന ഫോഴ്സ് will be negative. Okay, and whereas at B യിൽ നോക്കുന്ന സമയത്ത് ഇവിടെ സ്ലോപ്പ് എടുത്ത് നോക്കുകയാണെങ്കിൽ d by dx എടുത്ത് നോക്കുന്ന സമയത്ത് at any point you know that it's negative, it's less than 0, meaning that force is positive for any point that is on this side of the graph. Okay, and at the origin, at the point C, we know that there is no change. That is, u is a constant there, or u is 0 there, meaning that du by dx is 0 there, or f is 0 there. Okay, here at every point you have to remember that force is minus du by dx, right? Negative gradient of potential on force in or another line. Okay. And talking about the equilibrium point, we can actually have 3 kinds of equilibrium points. Okay, so this is the one kind, this is another kind, another kind. Okay, so in all points the common factor is that du by dx is 0, right? Because u is a constant at that point, so the differential will of course be 0, right? But look at those curves, they don't look alike, right? ഒന്ന് താഴോട്ടേക്കുള്ള സാധനം ഒരു കുഴി പോലത്തെയാണ്, മറ്റേതൊരു കുന്നു പോലത്തെയാണ്. No, the other one is quite stable, plain പോലെയുള്ളവരാണ്. Okay, അപ്പോൾ when you look at it, you know that ഇവിടെ ഓരോ പോയിന്റിലും സ്റ്റെബിലിറ്റിക്ക് വ്യത്യാസമുണ്ട് അല്ലേ? When you look at it, you know that ഈ ഒരു പോയിന്റിൽ നിൽക്കുന്ന പാർട്ടിക്കിൾ ആയിരിക്കും will be more stable compared to this one or this one, right? ഈ ഒരു പോയിന്റിൽ നിൽക്കുന്ന ഒരു സാധനത്തിന് മുകളിൽ അപ്ലൈഡ് ആകുന്ന ഫോഴ്സ് we know that the particle will start to execute SHM at this point, whereas ഈ ഒരു പോയിന്റിൽ നിന്നാണ് body displaced ആകുന്നതെങ്കിൽ it will move either to this side or this side. Force ഏത് ഡയറക്ഷനിലാണ് എന്നതിനെ ഡിപ്പെൻഡ് ചെയ്തിട്ട് it will move. Right? Here also it will start to move towards either of the sides. Right. So stable equilibrium points equilibrium points there are stable, unstable, and neutral equilibrium points. So this one right here, we have the first one is actually a stable equilibrium point. Right. This is an unstable equilibrium point. And this one is a neutral equilibrium point. Right. And how do you understand whether എല്ലാ കേസിലും നെസസറിലി നമുക്ക് ഗ്രാഫ് കിട്ടണം നിർബന്ധമില്ല. അപ്പൊ നമ്മൾ എങ്ങനെയാണ് ഒരു ഫംഗ്ഷൻ കിട്ടിക്കഴിഞ്ഞാൽ, പൊട്ടൻഷ്യൽ എനർജി ഫംഗ്ഷൻ കിട്ടിക്കഴിഞ്ഞാൽ അത് സ്റ്റേബിൾ ആണോ അൺസ്റ്റേബിൾ ആണോ ന്യൂട്രൽ ആണോ എന്ന് മനസ്സിലാക്കണം. ഓക്കെ, അതിനുവേണ്ടി നമ്മൾ ഡി യു ബൈ ഡി എക്സ് എടുത്തു കഴിഞ്ഞാൽ വി നോ ദാറ്റ് വിൽ ബി 0, റൈറ്റ്? സോ ദ നെക്സ്റ്റ് തിങ് ദാറ്റ് യു കൻ ഡു ഇസ് യു കൻ ടേക്ക് ദ ഡി സ്ക്വയർ യു ബൈ ഡി എക്സ് സ്ക്വയർ. ഓക്കെ, അത് ഈ മൂന്നെണ്ണത്തിന് ഡിഫറെന്റ് ആയി. ഓക്കെ, stable ആണെങ്കിൽ it will be greater than 0, meaning that it will be positive, whereas for unstable it will be negative. Okay, whereas for neutral it will be 0. Okay, so this is how you can find out whether the point of stability is an unstable, unstable, neutral, point of equilibrium. Okay, so this is the most important topic which you should be studying thoroughly. Okay, energy diagrams. So the importance of this portion is, it's very interesting. Potential energy. സാധാരണ നമ്മൾ ഫിസിക്സിൽ ചെയ്തുകൊണ്ടിരിക്കുന്ന കാര്യം, we are trying to find out the equations of motion. So, ഒരു particular point of time, the where it was, where it will be, എന്നുള്ള കാര്യങ്ങളാണ് നമ്മൾ കണ്ടുപിടിക്കുന്നത്. Most probably we'll be writing the equations for force, right? So here from this equation, what we have is energy, potential energy plotted against the distance, right? So here we have a curve, right? A curve that is in the form of a parabola. So this is a one-dimensional graph, right? One-dimensional graph, meaning that one-dimensional motion, not a one-dimensional graph. Sorry for that. It's a graph plotted for a one-dimensional motion because x directional markana on the position part, right? So say the particle has an energy that is equal to E, okay, maximum energy. I can't check it. So it can have an energy between 0 and E, okay, and that will be a sum of kinetic and potential energies, okay. And here ഇതില് ഈ ഒരു curve ഏത് പോയിന്റിലെയും slope എടുത്തു കഴിഞ്ഞാൽ what you will be obtaining is negative of force minus F, the value of force acting on that particular particle, right? Also that we know that the value for potential energy here in this case of a linear harmonic oscillator, which is equal to half kx square. And when you look at this, these are the two turning points, x1 and x2. Particle velocities is 0 on the points idan, or either kinetic energies is 0 on the points idan. And from that point, you know that particle it will start oscillating about this point, right? That's the case of the linear harmonic oscillator. Say we have a particle bound in here, okay? So every bound system oscillates like a harmonic oscillator to and fro about a particular point, and the acceleration will always be directed towards the equilibrium point, okay? So equilibrium point, if it is slightly perturbed, you know what path it will be taking, right? If the total energy is small, then the motion is restricted to the region, okay. ഇതിന് ഇതിന്റെ അകത്തുനിന്ന് ഈ ഒരു വെല്ലിന്റെ അകത്ത് we call this as a well, okay. So അതിനേക്കാളും energy കൊടുത്തു കഴിയുമ്പോൾ it could either go towards this side or it can escape towards this side, okay. If the energy is less than that, what it will do is it will execute a simple harmonic motion here, okay. So this should behave like a simple harmonic motion if the energy is less, okay. So these small oscillations in a bound system, we can mathematically explain it using a Taylor expansion, okay. So Taylor expansion even now about some point the function f of x എന്ന് പറയുന്ന ഫംഗ്ഷൻ എടുക്കുകയാണെങ്കിൽ അതിന്റെ Taylor expansion എടുക്കുകയാണെങ്കിൽ we can write it as f of x0 plus 1 by 1 factorial into x minus x0 f dash of x plus 1 by 2 factorial into x minus x0 square f double dash x, and it goes up to n like that, okay. So ഈ ഒരു Taylor expansion let's apply in the case of potential energy, okay. Here if the function is f of x, we'll take that as u of x, potential energy which is a function of the distance, okay. So this is at the equilibrium position, that is x0, okay. So you can keep on writing like this, f dash, since it is equal to du by dx, right? This is derivative, right? Second derivative it is. Then on. So we have to rewrite like this. Potential energy the case at equilibrium point, we know that du by dx is 0, right? So this term vanishes. The whole term becomes 0. Okay, so what is left is u of x0 plus 1 by 2 factorial into this one plus whatever we have there. Okay, higher terms in a നമുക്ക് neglect ചെയ്യാം since they will be very small number. Okay, we will have 3 factorial താഴെ വരും and d cube u by d cube ഒക്കെ വരും. So we can neglect higher orders. Okay, so what we'll be left with is ux is equal to ux0, this one and this one. Okay, so if x0 the potential energy 0 ഒക്കെ എടുക്കുന്നുണ്ട്, equilibrium point of potential energy 0 ആണെന്ന് എടുക്കുകയാണെങ്കിൽ, then we can write it as, then ux0 becomes 0, right? So this also becomes 0. Then what we have is 1 by 2 factorial x minus x0 square into d square u by dx square at x0. Okay, which is equal to 2 factorial is 2 itself, 2 into 1. 2 into, it is in the form of kx square, where this thing is a constant at x0 it is, right? So into x0, if we are to take it as 0, then this will become ux is equal to half kx square. All right, which is the equation for potential energy in the case of a linear harmonic oscillator. Or force acting on a particular body is equal to minus du by dx, which is equal to minus kx. Right? You can write it from the last equation. Okay, okay. Then now we have u equal to half kx square, right? Say, let's take the example of simple pendulum. Okay. Adinathu, we know that kinetic energy is equal to half mv square, right? Or half mx dot square, because x dot is v, right? And here omega is root k by m in a simple pendulum. ഇതിന് മുന്നേ ഡീറ്റെയിൽ ആയിട്ട് ഡിസ്കസ് ചെയ്തതാണ്. From there we know that the value of angular frequency is obtained as k by n. Right? അപ്പോൾ ഇത് നമുക്ക് എല്ലാ സിസ്റ്റത്തിലും ഇങ്ങനെ തന്നെ അപ്ലൈ ചെയ്യാൻ പറ്റും. സി ഇവിടെ നമുക്കൊരു ജനറലൈസ് കേസ് എടുക്കുകയാണെങ്കിൽ, സേ പൊട്ടൻഷ്യൽ എനർജി is half a q square plus c. ഇവിടെ q ആണ് വേരിയബിൾ. Here it is x, right? So here q ആണ് വേരിയബിൾ. Then kinetic energy equal to half b q dot square. See? അവിടെ നമുക്ക് angular frequency എങ്ങനെ എഴുതാം? Equal to root of a by v. Okay. That is it. And we have another example about molecular vibrations given in the text. So you can go through it. And if there is any doubt, you can actually ask, okay, individual WhatsApp clear it. Okay. And next we have in this chapter is non-conservative forces. So throughout this chapter, we've been talking about conservative forces, right? For non-conservative forces is that is known, right? So conservative force പറഞ്ഞ സമയത്ത്, if it does not depend upon the paths and if it only depends upon the initial and final points, it is conservative, അല്ലെ? അങ്ങനെയല്ലേ ഫോഴ്സിനെ പറഞ്ഞിരുന്നത്? Sorry, conservative forces നെ പറഞ്ഞിരുന്നത്. Now when we talk about non-conservative forces, if the work done by the force in moving a particle from one point to another depends upon the path, then the force is non-conservative. Okay. Viscous force ആയിക്കോട്ടെ, frictional force ആയിക്കോട്ടെ, these are all examples for non-conservative forces. These are things we have actually discussed in class. Okay. The conservative forces in the case, you know that there is a particular energy which is equal to k plus 2, right? In constant movement. And when we consider the change in kinetic energy, the change in potential energy, we got change in energy to be 0, right? Non-conservative forces in the case, right? That is not the case. Okay. So say W1 is the work done against non-conservative forces. Then we can write delta K plus delta U equals delta, this is delta E, right? and that is equal to W1. Okay, and non-conservative force is a frictional force ആണ് നമ്മൾ എടുക്കുന്നത്. Then it will appear in the form of heat energy, right? So Q ആണ് heat energy developing. We can write W1 to be equal to Q. Okay, അപ്പൊ നമുക്ക് ഇവിടെ ഡെൽറ്റ ഇ എന്ന് പറയുന്നത് എന്തായിരിക്കും? Change in energy will be Q, or we can write delta K plus delta U equals Q, or E delta E, sorry, ഇതിന് നമ്മൾ Qനെ നെഗറ്റീവ് ആയിട്ട് എടുക്കാം കേട്ടോ. So this one is negative, so plus Q, that will be equal to 0. Okay, ഇവിടെ നെഗറ്റീവ് വന്നതിന്റെ കാര്യം എന്താന്ന് വെച്ചാൽ work done by the body is against the frictional forces, right? So that is why we have the negative. Okay, so we can say that for all types of non-conservative forces, the total energy remains conserved. Okay, so here change in mechanical energy plus change in all other forms of energy, that is equal to 0, right? Okay, so this we can call as the law of conservation of energy. So the law of conservation of energy, so this law basically says that the total energy is conserved. Okay, so the forces that we see usually, that we deal with usually, that are whether it be the gravity or the electric and magnetic interaction, these are all conservative. Okay, so how does non-conservative forces arise? Okay, the thing is that the answer lies in describing a physical system considering the concept of energy. Okay, so frictional force example, it's a non-conservative force. So when a block slides across a table, mechanical energy is lost by friction, and the block and the table get warmer, right? So till now we have not introduced the idea of temperature while developing the concept of mechanical energy. Okay, so here what happens is that there is heating that's happening, right? അപ്പം ജെയിംസ് പ്രെസ്കോട്ട് റൂൾ ആണ് എന്ത് കണ്ടുപിടിക്കുന്നത്? ഹീറ്റ് is a form of energy എന്നുള്ള കാര്യം പറയുന്നത്. So yeah, so it is Joule who concluded that heat must be a form of energy, and also the sum of mechanical energy and the heat energy of the system is conserved. So basically, what the general law of conservation of energy says is that the total energy is conserved. Okay. So the next idea we have to discuss in this chapter, and the final section of this chapter, is about power. Okay. So power is basically the time rate of doing work, or mathematically divided as dW by dt, right? And dW we know as F of W, right? Divided by dt. So here it's dr by dt, right? F of dr by, or dr by dt is velocity. Yeah. So this we can write as F dot b. Okay. So this is the instantaneous power. Power in the unit എന്ന് പറയുന്നത് watt ആണ് അല്ലേ? Or SI unit എടുക്കുകയാണെങ്കിൽ it's joule per second. Yeah. So usually നമ്മൾ ഉപയോഗിക്കാറുള്ള ഒരു യൂണിറ്റ് ഫോഴ്സ് പവർ ആണ്, which is equivalent to 746 watt. Okay. So here we conclude the second chapter, and there are certain problems given at the end of your chapter. that is exercise problems unattended. So I want you to go through all of it. We wouldn't be able to discuss it here. They're all solved problems. Many of them are solved. You actually need not spend too much time with the unsolved ones, but you can try solve problems. And if there is any doubt, you can contact me. You can ask me, okay, through WhatsApp. All right, and I think we can wrap the session up now. So thank you for your patience. Thank you for listening.